So last time, these are the main points we discussed. We saw what is echelon form of a matrix, and we saw that our strategy to solve a linear system should be to try to bring the augmented matrix associated with our system to the echelon form. So always reduce the system to echelon form, and you will either find the solution or you will get to know that your system is inconsistent. If you encounter a row like that, it will be inconsistent, and you can use elementary row operations to get to the echelon form. And if you find that your system is strictly triangular, then you will have a unique solution, otherwise you will have infinite number of solutions. And then we saw the reduced echelon form, which is just a way of using, so you go to the reduced echelon form by using further row operations, and this is a way to perform back substitutions. So this is the easiest, the best you can do to read off solutions directly from your reduced matrix, reduced echelon form. So today we are going to look at some of these things. I will do some easy applications as well because I don't want to jump to the next topic today. I want to start it, those new things with a standalone lecture. So we will see what are overdetermined systems. So far we have been discussing the n by n systems, square systems, where number of equations is equal to the number of variables. So we are just going to discuss what if that's not true. What statements, general statements you can make about the systems. Can you find solutions, and what kind of solutions exist in those cases? So if you have more equations than variables, you call it overdetermined systems. You have many more conditions than you were expecting. And you have an underdetermined system if there are more variables but less equations. So just intuitively, it seems like that if you have an overdetermined system, you have a chance, you have a greater chance that it will turn out to be inconsistent, because you have a few numbers and you are putting a lot of conditions on them. On the other hand, for underdetermined systems, you expect that you will have many solutions. The unique solution will probably be not there or would be a special case. But it would be easy to satisfy few conditions with a large number of variables. Homogeneous systems are just systems which have all the constants equal to 0. So we have been writing our equations with the constants, those numbers without any variables, to the right hand side of the equations. If those numbers are all 0, then this would be called a homogeneous system. And a homogeneous system could be square, underdetermined, overdetermined, all those possibilities are there. So as we have been doing, let's start by looking at some examples of overdetermined systems. So you have m by n systems, m equations, n variables. Like in the first example, you have 3 equations and 2 variables. In the second example, you have 4 equations and 3 variables. So correspondingly, in the augmented matrix, you have here 3 rows because that's the number of equations, and 2 columns in the coefficient matrix. And then again, as always, you add an extra column for the constants on the right hand side. So for the m by n systems, you have m greater than n. So the coefficient matrix for these overdetermined systems will always have more rows. More rows, that's same as saying m is greater than n. More rows than columns. in the coefficient matrix, this part, on the left hand side of the dotted line. Now, because of this fact, you can make some general statements. So if I write some general matrix corresponding to an overdetermined system, I will have things like this. So let's say I'm writing a 3 by 5 system. This tablet is useless. Let me change the tablet. So you have these numbers in your matrix, and just an example I'm writing is as a 3 by 5, 5 by 3. Now, our strategy to solve these would again be, we are trying to eliminate as many variables as we can. So again, we are trying to bring it to echelon form. And when you try to bring any matrix to echelon form, what you have is that in each row, you have a lead variable. You start with this guy in the first row and first column, that you always want it to be non-zero. Then you make everything below it 0. In the next row, you will again, so you will find the lead variable. So what's the lead variable? The first non-zero variable. Let's not call it a variable. We call it variable when it's in the equation. The leading non-zero number in a particular row, what it would be, the first non-zero number after a bunch of zeros. So each row will start with some zeros, and then you will encounter a non-zero number. So the first non-zero number is your leading non-zero, and it's possible that you encounter it. It will never happen below the lead number in your previous row, because at each step you are sliding to the right. You start with a lead number and make everything below it 0. So in the next row, you will encounter the lead number at either this spot, or it could be, it's possible that you encounter a 0 here as well. Then it would be at this spot. So either this or this. So suppose it's over here. Then in the next row, you can have, your only possibility is that your lead number is over here, but this could also be 0 as well. But at maximum, your lead numbers are equal to the number of rows, because in each next row you slide it by 1. It is equal to the number of columns. Leading non-zeros are equal to number of columns, because in each next row you slide your column by at least 1. So at maximum, at max you can have n lead variables. and every number below the lead variables is 0. So this would mean that every row below the first n rows is going to be 0. So you will have m minus n rows which will be completely 0 in the coefficient matrix. So like over here, if this is lead, this is lead, this is lead, then necessarily these guys will be 0. So in an overdetermined system, at least m minus rows will be 0 in the coefficient matrix. This then leads to three distinct possibilities. Because you have m minus n rows which are 0, like over here, because n is equal to 3, so 5 minus 3, 2 rows must be 0. There's no other choice once you put it in the echelon form. Now, if you look on the other side of the dotted line, these numbers could be 0 or non-zero. So if any of these row, if this is non-zero, then you will encounter inconsistency. So what we have seen is that m minus n rows in the coefficient matrix have to be 0. This will always turn out to be true. But on the other hand side, it depends on the numbers. So for very special numbers, you will get zeros. Otherwise, you will get some non-zero number. So that means you have for a randomly chosen system, or for a randomly chosen right hand side numbers, there is a great chance that you will encounter inconsistency. So this is the reason that if you have an overdetermined system, unless something special happens to the right hand side, you will encounter inconsistency. But in this case, so we know that m minus n rows have to be 0. Suppose now you do not have an inconsistency. You are sure that you have a consistent system. Even then you have two more possibilities. You can have, there's no guarantee. There's guarantee that m minus n rows will be 0, but there's no guarantee that not more than m minus rows cannot be 0. So these two rows are guaranteed to be 0, but as we have seen previously, it's possible that you do not encounter a non-zero number here. It's possible that you get a 0 here. Then you move to the next column, and then you hope that you get something non-zero here. Then this is your leading non-zero number, but then everything below it becomes 0. So this guy also becomes 0. So then you can have this is always true, more than m minus n rows completely 0. There was a possibility that you had a non-zero here, but this could be zero. This could still be zero. That was also a possibility. But the point is that you always can have more than m minus n rows to be zero, but at least m minus n have to be zero. Actually, this statement, this is a general statement. It doesn't have to be true when m is greater than n. It's true when m is equal to n as well. So when this is true, you have more than m minus n rows to be zero, then you have like n variables, but more than m minus n rows to be zero, then some variables will be free variables. So like over here, when this guy, the third variable is free, while if I make this zero and this non-zero, then this variable x2 becomes free. Then you have free variables and hence infinite number of solutions. But you can have the least case scenario as well, that you have exactly m minus n 0 rows. Then you will have no free variables and a unique solution. Because then your matrix would essentially be, you can neglect these 0 rows. All the information is contained in this block, which is exactly triangular. So then you will have a unique solution. So let's look at the example which we discussed over here. So this was our first example. And I'm just going to bring it to echelon form. So this goes to multiply by -1 and add to the next one. And then add it to the third row. Now, this guy, you have to make, this is the lead variable, you have to make everything below it 0. But before doing it, because I'm bringing it into echelon form, let's make it 1. Then it's easier to add as well. Multiplying by -half. So once I have done it, I'm just doing the next step directly. So I have a minus, so I multiply it by -3 and add it to the next row, which is this row. I get 0. Minus, multiply by -3, I get a 3, 3 and plus -1, I get a 2. So this part is what we know will happen. That you have 3 rows and 2 columns. So 3 minus 2, 1 row has to become 0. But on the right hand side, I did not get a 0. So it's inconsistent. इसको explain कर दूं? हाँ? Yeah, I guess this should be now pretty obvious what we are doing. I multiply this row, the second row over here by minus half to make it 1 minus 1. Because in the echelon form, I want a 1 as the leading non-zero. So once I have a 1, then I'm making everything below it 0. The second matrix now I'm not gonna perform the calculations. I'm just gonna write what you get as an answer. So it's kind of obvious that you have a lead, then zeros below it. Then the next lead and zeros below it. Next lead, zeros below it. So this row has to be 0. There's no other choice. If you do the calculation, that's what you find. Zero, 1, and this row is 0. Because you are basically doing it by hand, by construction. For this system, it was very specially chosen. So you do get a consistent answer because the 0 has a 0 in front of it. And the rest is a triangular system, so you will find a unique solution. Let's look at this example. Again, 3 variables and 4 equations. So 4 rows and 3 columns. When you do, so this I can put right away 0. But what I find, because nothing is stopping this to happen in some cases, that you don't get any lead variable here. This becomes 0. But fortunately, on the right hand side, again, you have zeros. So it's consistent. And can you tell me what's the free variable here? Third one. Because this is the leading number corresponding to, so the lead variable, first lead variable is x1. Here the lead variable is x2. And here the lead variable is, x3 is not a lead variable. If I had a 0 here, and a 1 here, and let's say to make it consistent, well, this is also consistent, but let me just change it a little bit. So now x2 is free because this is the over here, this is the lead, and in the next row the lead comes at the third column. Now the underdetermined systems just have like less conditions than the variables. So this time, this is a short practice because it's going to be very easy to solve them. Let me try to solve both of these. So when I do this, -2 plus 2, -4 plus 4, 0, -2 plus 2, 0, -2 plus 3 is 1. So this one turns out to be inconsistent. So it's possible even in this case for systems to be inconsistent, although we are expecting that we have more variables and less conditions, so it's kind of easy, should be easy to satisfy them, but it's possible that your condition is special, that it gives you inconsistency. Very soon we're going to understand all of this, that how does these inconsistencies arise. And for the second system, the matrix is 1, 1, 1, 1, 1, 1, 2. Then 1, 1, 1, 2, 2, 3, 1, 1, 1, 2, 3, 2. So now just multiply by -1 and add to the next rows. I'm doing these examples because I don't expect everyone to look at the tutorials, although you should, but since I made those optional, so -1 plus 2, 1, -1 plus 2, 1, -2 plus 3, 1, 0, 0, 0, 1, -2. This was -1 plus 2, which gave me 1, -1 plus 3, 2, and -2 plus 2 gives me 0. And this time I encounter zeros here, so I keep moving to the right until I find a lead, and then I make the numbers below it to be 0. Am I correct here? What I have written in my notes is a little different. So -2 plus 3, 1, -2 plus 2, 0. Okay. 1, 1, 1, 1, 1, 2. You're not touching the rows which you have put in the correct form. So just -1 and add it to the next row. -1 plus 2, 1. -1 plus 0, -1. So you have got the echelon form. Now this is the echelon form. And you can see that x2 and x3 are free variables. x1, x4 and x5 are the lead variables. Now if you want, you can back substitute. Back substituting means that I take my lead in each row and make things above it 0 as well. That won't change in the above row, increase before it. -1 plus 1 gives me a 0. -1 plus 1 gives me a 0. -1 plus 2 gives me a 1. Now let's just make this lead variable and increase above it 0. -1. In the first row, things are already in the correct order, so not gonna change that. But take -1 and add it above. -1, -1, that's 2, 2 plus 1, 3. Is it correct? And this is a 1. So you have got your solution. x5 is equal to -1, x4 is equal to 3, and x1 is 1 minus beta 1, beta 2, where beta 1, beta 2, you can give them any values. And x2 and x3 can be anything. So we saw these two examples. In one it was inconsistent, in one we had infinite number of solutions. If you think about it, you have m rows and n columns, and n is bigger than m. Now since you have this is wrong. Yeah, no, this is correct. Lead variables. So in each row, you can have only one lead variable. A row cannot have a lead variable. When it will not have a lead variable, when it will be completely 0. When it's not completely 0, the first number you encounter is the leading number, and if you encounter it in, let's say, rth column, then the rth variable is the lead variable. Now over here, like you had only 3 rows, so you can only have 3 leads for one lead for each row. But you had 5 variables, so 2 had to be free. So that's what's written over here. Since you have m rows, so at maximum you have m lead variables, but you have more columns. That means you have more total variables. So you have n minus m free variables. But it's still possible that you don't have M leads. You have less than M leads. Some row by chance becomes completely zero. And on the other hand side of it, you encounter a non-zero number. So you can have an inconsistency like we had in our example. But if you don't have an inconsistency, then you will necessarily have an infinite number of solutions. You cannot have a unique solution. So any question? Yes. So homogeneous systems are just of this form. You have some numbers. Let me write a square homogeneous system just for a change. This is the coefficient matrix. So this last column in the augmented matrix, if this is zero, then you just call it homogeneous system. Otherwise, there is no restriction on how many rows you have or how many columns you have. So my claim is that it's always going to be consistent. Why is so? Because when the only way you encounter an inconsistency is that when you bring your coefficient matrix to the echelon form, you encounter, if you encounter some zero row, and on the other hand side, you do not have a zero. That's the only way you can have inconsistency in your linear system. But since the right hand sides are all zeros, if you multiply, if you do any row operation, under any row operation, the last column does not change. That means if you create a zero row in the coefficient matrix, on the other side of it, it will still be zero. So you cannot have inconsistency in a homogeneous system. Always has a solution. Actually, you can tell me one solution right away. What would that be? I give you any homogeneous system. Let's write an example. 3x1 plus x2 minus x3 is 0. 2x1 minus x2 plus 6x3 is 0. x1 minus x3 is 0. Can you tell me one solution?
Sir, x1 is equal to x3.
Yeah, the last
X1
one says
is equal
x1 is equal to x3, but I want numbers. I want one particular solution. You're just looking for three numbers which will satisfy this equation. If I take x1 equals to 0, x2 equals to 0, and x3 is equal to 0, that's obviously going to satisfy the equation, because on the left hand side I do not have any constants, only addition of all these variables with some coefficients. But as long as I take all these variables equal to 0, I get the zeros on the left hand side. And since right hand side is already zeros, So I always have this solution available. So one solution is always possible, but many a times you are interested in, so this is called a trivial solution. Many a times you think this is way too simple. You have a system and you want some numbers. You are computing some quantities and you want some non-zero answers. So then you are after non-trivial solutions. So non-trivial solutions will be possible. Again, since it's always consistent, and we saw when we made this general statement that when you have m is greater than n, then you will have when, wait, one statement I want to make over here. So the previous statements which I made, they still stand. That if you are able to reduce it to, if you have m is greater than n, and you do not have as many zeros, you have more zero rows. So for example, if I go over here, if n is greater than m, then some of the variables are free. So so if they are free variables, you can give them any value. So you immediately have some non-trivial solutions over there. So many a times you do have non-trivial solutions, but one trivial solution is always possible. Now let me do some more examples, more in the line of some applications, just to see them in action. So these are taken from the book. This one was a problem in the book. So suppose you have an intersection of roads. These are all one ways. Traffic can only go in one direction. And suppose you have sent out someone to take some data about the traffic along this intersection. You are planning for, you're tasked with planning, traffic planning for the city, and you send someone to take some data. And they're counting how many cars on average cross each of these roads, let's say per hour. So they come back, they said that they have observed the traffic for many weeks, and per hour, this is what they find. So this is a one way going this direction. This is a one way going this direction. This is one way going this direction. This direction. This direction, this way. and this way. So they tell you that there are 380 over here, 430 here, 540 coming from this direction, 420 going out this way, 450 going in from here, 400 coming out from here, 420 on this branch. But they say, disappointingly, I couldn't really count how many were here. There are way too many things to do, too many cars to count, so I couldn't count these. So these are unknown. You say that, well, I already have a lot of information about what's going on here, so I can try to find these unknown numbers, x1, x2, and x3. So how can you write down some equations? Well, you can look at this intersection. The numbers of cars entering must be equal to the number of cars which are going out of this intersection, right? So you have x1 plus 380 is equal to x2 plus 430. Then over here, did I write a number for this one? Well, this is also not known. It's 4, and this is 470. So and then I move to the next intersection. The cars going out are x1 plus x4, and the cars coming in are 420 plus 450. The next one, x3 plus 470 are coming in, which must be equal to the cars going out. And over here, x2 plus 420 is equal to, no, x2, sorry. So x2 is going in and 540 is going in, which must be equal to x3 plus 420. So I can build from these equations, build a matrix. पहली इक्वेशन से क्या आ रहा है 1, 2 का coefficient -1, because I am bringing the that's how we write it. Bring the variables on one side and constants on the other side. For x3 I have 4 variables. x3 and x4 do not appear, so they are 0. And I left it on this side, so I get a 50. Then I get a 1, 0, 0, 1, and 870. Then I get a 0, 0, 1, 0, and 350, right? Because 420, I take it to the other side, I get a -70, so 350. Then I get a 0, 1, -1, 0, and -120. no, minus 120. So all you need to do is bring it to echelon form. You can do anything, but I can do it in any order. But since I have a lead variable on the first place, so I know that the first equation is fine. So let's start from there. 0, 1, 0, 1, minus 50 plus 870, that gives me 820. 0, 0, 1, 0, 350. Now I see I don't need to swap anything because I already have a lead variable here and I just need to make this 0. So minus 1, 0, 0. Minus 1 times this. 0, minus 1, minus 1 plus 0, minus 1, minus 820, minus 120, that gives me minus 940. Is this correct? Now I just have to add these. This gives me 0, this gives me minus 1, I can multiply it with a 1 to get 940. So I find no inconsistency, no 0 row, so I know that I'll have a unique solution. I have put it in a triangular form. So I'll get exact answers for it. And I know that x4 is 940, x3 is 350. I can bring it to the echelon form and I'll have the answer from here as well for the back substitution. This is the echelon form. Yeah, I can do that, but I'm just going to save some time. Let's set up some other example. Should we take one from circuits or economics? Do you guys learn about circuits in any course? Huh? Huh? Not logic gates, like solving for currents and voltages. So let's do one. Let's first do one with economics and then circuits. I'm just going to set up the equations. No, we don't need to solve them. You can do it. So suppose you want to set up a very simple monetary system. Some kind of you want to invent a currency. and you have some barter going on between these three types of industries. So let's say you have farmers which are producing edibles, you have some manufacturers who produce tools, then you have some people who are producing clothes. And to survive, as it usually happens in villages or used to happen, people used to just exchange these goods. Okay, I grow some things, I'll share it with you, and you make some tools for me. Now, suppose these guys, instead of always counting how many I have given to you, they want to create some currency to keep track of their trade. And they want to represent the bartering which they had agreed on is the fair bartering system. They want to represent that. So what happens is, whatever the farmers produce, they keep half of it for themselves. They give uh, 1/3 to the manufacturers, and they give 1/4 to the cloth makers. Then these guys So what are you having over here? So you have things like 1/2 x1 plus 1/3 x2 plus 1/4 x3 is equal to x1. Similarly, you can 1/4 x1 plus 1/3 x2 plus 1/4 x3 is equal to x2. So when you will fill up these three equations, you have a 3/3 system, and when you bring them on the other side, you will have a homogeneous system. But the problem is with this homogeneous system is that when you bring it to the echelon form, then it better have a zero line. Because if it doesn't have a zero line, then it will have a unique solution. And we know that a homogeneous system always have one solution, which is 0, 0, 0. So if they are not trading anything, that's okay. That would be 0, 0, 0. So you are creating a currency with zero value. But If you have a zero line over there, then you can find non-trivial solutions. And then you can choose some units of this currency. And one will be given, x1 will be given, x1 and x2 will be given in terms of x3. Because if you have one zero line, then one of these will be a free variable. So then, for example, you can write x1 and x2 in terms of x3. So if the products which are represented by x3, you give them 1 unit of currency, then you would know that how many units you have to assign to x1 and x2. So you are pricing these products with your invented currency. Now let's look at some circuit analysis, and if you haven't studied circuits, you can ignore this example, but it's very kind of easy. You can understand it in a minute that what goes on in circuit analysis. Actually not much. So you have some resistances over here. So this is like those who haven't studied any circuits. This is like you are putting in some bulbs, electric elements in your circuit. And depending on how many power your electric element consumes, you have a certain resistance associated with it. And those units for resistance are the ohms. And these are some batteries. They have some wattage. Eight volt, 9 volt, you all have seen these ratings. Now, there are two laws of circuit analysis called Kirchhoff's laws. So what these laws say is the following. So you have certain currents going in. So this is like the traffic example we did. I'm giving them some names, and you can give any direction to these currents. The direction will come out in our solution. Some current is flowing. So at this node, this current is dividing. I1 is dividing into I2 and I3. So the law says that as much current as goes in must be equal to the current which goes out, just like traffic. Because current is nothing more than flow of electrons. So current going in is equal to current going out. So if I use that, I get I1 is going in and I3 is going in. That must be equal to I2. And on this node, I2 is going in. The current is going, I have given it this direction. So that means I1 is going out. And I3 is also going out. So actually, this doesn't give me an extra equation. This is just gives me the same equation back. So let's cross this out. The second law says that when you pass through some electric element, you lose some voltage. So this is called the voltage drop. So to keep the current going, that's why you lose some voltage, you need to provide some battery. You need to provide some voltage constantly. So when you pass through a battery, you gain some voltage. and that voltage is then dropped or used up in your electric elements. So voltage gain in a loop is equal to voltage drop. So like you have to choose a loop, choose this loop, then what you get is you gained 8 when you go this in this direction, and then you drop. How much you drop? It's the current times the resistance. Minus, sorry, this is I2, and in this branch I have I1. Similarly, I can use this, or better go this way because I have to follow. It would be easier if I follow the direction of current. So I get 9 minus 3 I3 minus 2 I2, and then I encounter this guy, which is again I3 minus 2 I3 is equal to 0. So in the end, what I have got is 3 equations in 3 unknowns. And it's not a homogeneous equation. And you can just try to solve it using your usual methods. So these were just some examples, like that these various different kinds, I don't have time to solve it, but these various different kinds of equations which we have encountered, they do show up very, very commonly in your everyday problems. So is there any question? Oh, because there were no constants. Because there was no, like, whatever they produced was shared between them. There was just the logic was such that there was no constants over there. Any other question? So let's stop here because next time I'm going to start with some new topic. So essentially, you know now the method of solving. From now on, we will try to make that these different possibilities which we have come across, and we know that once we solve this system, which one would be there. But we want to make general statements that even before solving, what we can tell and what's the intuitive reasons for these different possibilities to arise in your equations.